Just got off a presentation by John Preskill about machine learning and quantum information processing. And the lecture was about some work that he's doing where they try to predict quantum systems with classical machine learning, which is, fundamentally a really interesting idea, somewhat oxymoron-ish, if that's a word, because if you think about the quantum system and some of the analogies that Preskill himself is using, for example, the analogy with the book, where that it says you can't read the book page by page. You can only understand the book as a whole. But then he's saying that you can actually predict a couple of pages by looking at a few less pages. In other words, there's information in the subsystem. And I need to clarify this. He's going to give a public lecture tomorrow again, so I'm going to clarify this. I think what I want to discuss here is just this idea of classical machine learning for quantum and quantum for classical machine learning. This is not even on podcast. It's May 27, 2024. This is Krim Delco. For the day, the fund is up 1.25%. The market's up 7 basis points. For the year, we are down 9.5%. The market is up 11.5%, but underperforming by 21%. Just real quick, before I go into the discussion, today's performance is actually driven by NVIDIA, which was up quite a bit again. And I think it's about time to start thinking about long-term ideas about NVIDIA and how this company and the stock are most likely to evolve. The reason we're saying that is that given the 130% performance year to date, it's conceivable that some of the thesis that we had a couple of months ago about NVIDIA now is, let's say, getting stretched. And in order to hold on to the stock or think about it, maybe in terms of maybe we want to add more or reduce or things like along those lines, I think it's worth now thinking, just sitting down with a fresh, clean piece of paper and just think about what this company could become in the next 5 to 10 years. This podcast series is the purpose of this podcast series is to give people a sense of what it feels like to run a hedge fund, and we are in a position here where we have a performance which is similar to the one that Tesla had 3 years ago now, where the stock kind of went up 10x in a very short period of time, and we learned a lesson there. I mean, we should have obviously sold at $420 a share and then bought it back at $100 a share. This would have been prudent risk management. We didn't do that, and I think we are at a point here with NVIDIA where it's worth maybe thinking about not necessarily selling or anything like that, but just rethinking the position. Let's get to the conversation now. John Preskill, he's, I explained it to my son. I would say he's the sort of the Heisenberg of quantum computing, still alive, which means a founding father of a field, not the founder, not the initial spark, certainly not, but he is definitely consolidating a lot of the, a lot of the knowledge, and more importantly, also he is a very suitable liaison between practice, popular science, and professional science. What I mean with suitable is that he's not a science popularizer. He is deeply entrenched in the business of professional science. He's professor for theoretical physics at Caltech. He's writing very important scientific papers around the field. But he's also talking about the field to a general public, which this lecture, the lecture here at Stanford, is just one example of. But he goes to industry conferences. I've been following quantum computing now for about 6 years, including courses and conferences and interviews and summer schools and winter schools and all kinds of things. And I've been, I would say I've been led pretty well by the field. The field is open, the field is prolific, the field is transparent, and no matter how complex the field is, it's still very interesting. and it's also approachable. Excuse me. Now, Preskill is he's in the sort of, I would say, if you take this is just a tangent. If you take, let's say, science popularizers, you have, let's say, on the one spectrum you have, Neil deGrasse Tyson. Then you have people like Joe Rogan or Lex Friedman who are interviewing scientists with the pretext of trying to understand it. And then you have maybe people like Sean Carroll, who is, I would say, if the side with the Neil deGrasse Tyson's is, I would say, it's popularizing journalistic work with a little bit of science involved. And then there's a sort of a demarcation line, and then you go more to the science side, and John Carroll's certainly on the more science side, but still very, very popular by choice. There's nothing degrading there. That's just his choice of how he wants to communicate. He doesn't shy away from explaining complex methods, but he's not using the language of mathematics, for example, in his explanations by choice, because he doesn't want to scare away people. Versus John Preskill would be more on the more science side, where he's using the language of mathematics and he's using typical scientific tricks or tools, such as he would say, let's say, a Rydberg atom can be used for quantum information processing. He wouldn't go and explain what a Rydberg atom is. He would assume that. He would then continue in a more general way, trying to understand what that means. But he wouldn't go into details. So his lecture is about how can we use classical machine learning to understand the evolution of quantum systems. So let me parse that a little bit. First of all, what is classical machine learning? That's basically the machine learning that we all talk about every day. So this goes back to the neural network guys, Jan LeCun, Geoffrey Hinton, and Joshua Bengio, and then Andrew Ng, and Fei-Fei Li, and so forth, Chandra Malik, and then later on Sergey Levin and Peter Abil. So I'm just using the people that I'm familiar with. Of course, there's many other people I didn't mention here, but the idea is, okay, you have data, they get fed to an algorithm, the algorithm processes the data in a structure of a neural net to then approximate a function, and then when you give it new data, it can make certain predictions or solve certain problems. This is kind of this is the classical machine learning that we are all talking about today. Applied to image classification, it's being applied to predict sales, it's being applied to full self-driving in Tesla, it's being applied to many kinds of tasks where you have what's called inference, where you look at certain data and then you try to make a prediction based on that. So the input is hopefully making you some prediction for some sort of output. So Preskill wants to use this classical machine learning to make predictions for quantum system. What does that mean? What is a quantum system? A quantum system is a system at its lowest level, the known lowest level. So that's a level below the classical system. It's the level at which nature computes. A quantum system is, for example, a hydrogen atom and its behavior. And when we talk atom, we talk nucleus and electron. Let's not go deeper. Let's not go into quarks and neutrinos and things like that. But how does this system behave? There's something called the Schrödinger equation, which captures the wave function by which this system behaves. There's something else called an Hamiltonian, which is all the energies together, sort of the energy operator, which is, think of it like, let's say a car, a Hamiltonian of a car would be the kinetic energy, the friction, the air resistance, things like that. So we just capture everything in a Hamiltonian, all these energies together. All these energies can be expressed in certain vectors, and now we're trying to predict how this system evolves. And we can use quantum information processing or quantum simulation to see how the system might evolve in actual real time. So we can use the system for real and see how it evolves. Or we can use quantum information processing, which is we can sort of initialize the system and then simulate how it might evolve in real life through a model, and then see how that looks. And that's kind of where quantum information processing lives today. And since we have trouble building quantum information processing systems that can last for a long time, that can process algorithms in enough length and at time scales that are useful for us, Preskill is suggesting machine learning. So he's suggesting that we take, let's say, a quantum system. Let's say we take a couple of hydrogen atoms. We try to measure their ground state, or the closest we can get to the ground state. We try to capture that data, feed it into an algorithm. Preskill has developed an algorithm for that. There's a paper attached in the show notes that explains that. And that algorithm now predicts the evolution of that system. So what Preskill here is suggesting is really what I believe the science of the future will look like, which is instead of trying to explain the system, instead of trying to create the quantum system, we're feeding the machine data so it can help us design the quantum system. The AI is helping us predict the evolution of the quantum system. So we're not very good at creating the quantum system yet, but we might use AI to help us design the process by which the quantum system evolves. What is this useful for? For example, material design. This is one of the canonical examples of quantum systems. So we have, let's say, a bunch of atoms, lithium atoms, cobalt atoms, iron atoms. We try to design a battery with higher energy density, higher power density for better electric cars, or even better electric aviation vehicles, things like that. So how can we do that? Well, the design space is large because there's many ways we can iterate around these materials. We can put elements together in many ways. If we knew how their quantum systems evolve, then we could design them in a way and then connect that to the properties that we're looking for, again, higher energy density. We could use some of the, let's say, Joshua Bengio techniques, variational inference, and the sort of Monte Carlo tree type solutions that I discussed in a couple of episodes before this one. Basically think about it this way, like we don't know what all the possible design space looks like for our quantum system. So we can't really use probabilistic models because we would have to normalize this against all the possible. So if you want to have, let's say, the probability of X being high, let's say if the probability of a certain design formation is high, and that certain design the probability of a certain design formation being delivering certain properties is very high, we would have to know all the possible design formations to calculate the probability. Since we can't do that, we have to use variational inference or approximation, numerical methods to approximate certain pathways, trajectories towards solutions that could deliver us higher properties. So this is kind of what material science looks like. Now, there's other applications for quantum processing beyond material science. But in general, simulating nature is really one of the low-hanging fruits here. And John Preskill's methodology could help us simulate nature. Before I end, I just want to add one more Q&A part. I asked Preskill whether he thinks that quantum information processing has anything to offer for classical machine learning, so the other way around. And his answer was not really, that he was more excited about this 5 years ago. And he thinks that today, machine learning, classical machine learning, and quantum information processing are really two fields. There is not a lot of cross-pollination. Now, this might change, and I'm a little bit skeptical about this answer, and I would like to dig a little bit deeper. But it looks to me that Preskill is slightly disappointed about the prospects of quantum information processing, because one of the things that I thought could be used in quantum information processing for machine learning is the parallel compute. And it looks like Preskill, one of the experts in the field, disagrees with me on that one. So to summarize, I think the most important question about this presentation, in my opinion, is the following. Look, if you have a quantum system that is, if we use the book analogy, it's information in the system. So the individual parts, the individual pages of the book can't be read to understand the book. You have to read the whole thing. But then you're telling me that by reading certain pages, you can still predict a couple of other pages, maybe not the whole picture. Then the question here is, what is a page? In other words, what is the largest entity that you can predict or that has information still by reading individual pages? So how far can I go with the individual page reading, or what's the unit of analysis here? What do we call a page? How far can certain information get me before I lose the big picture?